Today, we are going deep inside the design of isolated, off-grid PV diesel hybrid systems right out of our Chapter 3 session. We're going to move from core theory straight into a massive, real-world case study. If you've ever wondered how engineers calculate the exact sizing steps for power equipment, manage complex control diagrams, and integrate massive solar arrays, BSS units, and diesel generators without a utility grid, well, you are in exactly the right place.
Here is our roadmap for today. We'll start with the PV diesel hybrid paradigm, move into sizing the power equipment, cover hybrid control and wiring, and finally dive into our 490 kilowatt peak case study.
All right, part 1, the PV diesel hybrid paradigm, creating an energy island. Let's get started.
To start things off, we have to completely shift our mindset away from standard grid-tied setups. Building an isolated energy island is just a totally different beast. Notice the stark architectural difference here. In a standard grid-connected plant, the utility grid is your master reference bus, right? Your inverters are essentially just slaves to it. But in a PV diesel hybrid, there is no grid. The system is its own isolated island, and here the hybrid controller is the absolute master. It dictates everything from breaker switching to zero export.
Think of this control architecture kind of like a symphony orchestra. The hybrid controller, that's your conductor. The diesel generator sets the rhythm, and the PV and batteries fill in the melodies. But the golden rule here is centralization. You can literally never delegate the control of the generator's safety-critical functions, like engine speed or voltage stability, to an inverter. The hybrid controller has to maintain total, centralized authority to keep the island stable. Moving right along to Section 2, sizing the power equipment. Let's break down the core math.
Okay, so the diesel generator is the backbone of your system, but you absolutely cannot just look at the nameplate rating and call it a day. When sizing your DG, you have to apply these 4 critical D rating factors multiplicatively. You've got ambient temperature, fuel quality, nonlinear loads, and crucially, motor starting, or locked rotor current, because motors can draw up to 6 times their running current at startup. If you undersize the generator, it fails during inverter inrush. But if you oversize it just to be safe, it runs at a dangerously low load, and that causes wet stacking, a devastating buildup of unburned fuel that will literally destroy the engine over time. It's a massive balancing act.
Next up in our sizing steps, we calculate the BESS, the Battery Energy Storage System. Looking at the exact engineering workflow here, first you determine your battery amp hours based on daily energy and depth of discharge. And by the way, lithium-ion LFP batteries are the industry standard here for their thermal stability. Once you lock in that capacity, you calculate your required PV power using a 1.3 nominal ratio for system losses. Finally, you size the power conversion system and your grid-connected inverters, usually adding a 50% margin to handle peak loads without tripping.
All right, Section 3, hybrid control and wiring. This is the nervous system of our energy island.
So we have the muscles sized, but they need to communicate flawlessly. The energy management system executes a really rigorous power priority sequence. Priority 1 is always solar PV feeding the load. Surplus solar, that moves to priority 3, charging the BESS units. The diesel generator is strictly priority 4. It's basically a last resort that only auto-starts when the battery hits a critical low. This specific logic maximizes your solar fraction while completely preventing that catastrophic wet stacking we just talked about.
But how do these commands actually travel across the site? Check out this single-line diagram and communication map. The data logger is the communication bridge. The load CT detects power flows, sends that to the hybrid controller, which then computes a set point and fires a curtailment command to the logger via RS-485 Modbus. The logger relays it down a daisy chain to all the inverters. The whole system can drop generation to match the load in a blazing fast 200 to 500 milliseconds.
Now listen up, because this is a massive warning for the step-by-step wiring connection. The RS-485 cable has a metal shield. You must ground that shield at the controller end only. If you ground it at both ends, you create a massive ground loop. It will completely scramble the Modbus signals. And if your controller can't talk to the inverters, your entire energy island collapses.
And speaking of physical wiring, the absolute first step is high-stakes safety. You have to lock out all grid, generator, and DC sources before a single wire is energized. Remember, power here flows from multiple directions: the solar plant, the BSS units, and auto-starting DG. Because of that, verifying zero energy with a multimeter is a life-saving, non-negotiable step.
Let's move to Section 4, the case study. Time to look at our 490 kilowatt peak masterpiece.
Let's actually put all this design theory into practice on a real commercial and industrial facility. This system operates entirely in island mode, zero utility grid connection. The engineering drawings delivered for this project had to be flawless, accounting for massive physical footprints and incredibly precise control diagrams. When you're building fully autonomous energy management, there's just no room for error.
Here are the final engineering deliverables for the project. For the PV plant, we have 792 modules, giving us 490 kilowatts peak. We balance that DC capacity with 415 kVA inverters for 460 kilowatts of AC capacity. We paired this with two massive 215 kilowatt-hour BSS units. And finally, based on our strict D-rating steps, the diesel generator was precisely calculated at 500 kilowatts, enough to handle the inrush, but loaded enough to avoid wet stacking.
Now, looking at the EMS architecture, it's meticulously configured. Motorized 4-pole breakers are mandatory here for neutral switching. We've got a load CT detecting reverse power to trigger PV curtailment in just 200 milliseconds to prevent backfeeding the generator. Plus, the UPS for the hybrid controller is explicitly tied to the generator side of the transfer switch, so the controller never ever loses its master authority.
So why do we go through all these intense calculations and drawings? Well, here's the payoff. By running that diesel generator at a 30% baseline and letting the solar and BESS units handle the rest, this exact system design saves the facility roughly $158,000 a year in fuel costs. The system pays for itself incredibly fast, while totally saving the engine from wear and tear. It's just brilliant.